In this video, we're going to take a look at section 4.3, which is on rules of logarithms. The first couple of rules we're going to look at excuse me, are the inverse rules. And we talked about this a little bit in the video on section 4.2, that logarithms and exponential functions are inverses of each other, which means they cancel each other out. Just like addition and subtraction are inverses of each other, they cancel each other out as well. That's how logarithms and exponential functions work. But the way they have to interact in order for them to cancel out is a little bit weird. It's not like adding and subtracting, unfortunately. So for a logarithm to cancel out with an exponent, the logarithm has to be in the exponent of the exponential expression. So here we have a raised to the power of log base a of x. And what's important here is that the bases have to be the same for both of them, right? So the logarithm needs to be in the exponent and the bases have to be the same. And if those two things are the case, then the base of the exponent cancels out with the logarithm of that base. And all you're left with is x, which here is kind of up in the air. It's up in the exponent, but when these cancel out, it just falls right down to the ground. That's the way I like to think about it. Conversely, for an exponent to cancel out with a logarithm, the exponential expression has to be inside of that logarithm. And again, they both have to have the same base, and then they cancel each other out. So here we have log base a of a to the x power. The log base a cancels out with the base a of the exponent, and we're just left with x, which again drops down to the ground. All right. So, excuse me, exponents and logarithms cancel out with each other in this particular way. So these problems are actually pretty easy when you do these on the homework because everything just kind of cancels itself out. So here we have 10 raised to the power of log base 10, right? The base isn't written here, so we are to assume it's base 10 of the square root of b. And that part makes it look more complicated than it really is. What's going to happen here, using the rules that we just looked at, is that the base 10 exponent cancels out with the log base 10, and we just get square root of b as a result. So the base of the exponent, the logarithm of the same base, cancel each other out, and whatever's inside the logarithm is all that you have left. All right, the same thing's going to happen down here. We have natural log, which remember from the previous videos, that's log base e of e to the 3x power. Whoops, I kind of messed up on that parentheses. All right, and then just like we saw in the previous screen, the base e logarithm cancels out with the base e exponent, right? Because this is inside the logarithm, they'll cancel each other out. And all that will remain is just 3x. Right. So everything cancels out and you just get whatever's left over. I guess I shouldn't say everything cancels out, but the exponent, the base of the exponent cancels out with the logarithm, and whatever's left over is your answer. All right. Now here's where things get really interesting. So we have the product rule, and it works this way. If you have log base a of m times n. So it's important here that you are multiplying the two things together, right? M times n. That's why it's called the product rule, because we're multiplying there inside the logarithm. This can be rewritten as log base a of m by itself plus log base a of n. And so what's happening here is we can rewrite this single logarithm as two separate logarithms where each of the things we're multiplying here go inside of its own logarithm. So the m gets to have its own logarithm, the n gets to have its own logarithm. What's really interesting and what makes this kind of hard to manage is that here you're multiplying the two things together, but when you write them in separate logarithms, you will add the separate logarithms together. And that throws a lot of students off. The reason this rule works is, as we mentioned in section 4.2, logarithms are exponents. They represent exponents, right? So log base a of m is how many powers of a it takes to equal m, right? So this logarithm here is this exponent. That's what the logarithm is representing. It's representing that exponent of how many powers of a it takes to equal m. This logarithm here, same thing. It's how many powers of a does it take to equal n. If you're going to multiply these two things together, what would you do with these exponents? You would add these exponents. So that's why this becomes an addition, because logarithms are behaving the way exponents would behave. If we're multiplying two things together, we would add the exponents. Therefore, we add the logarithms because the logarithms are the exponents. Right? So that's kind of a quick justification for why that rule works the way it does. The rule also works in reverse. So if you're adding two individual logarithms together, they can be added into a single logarithm, but you will multiply together what was in the original logarithms. So again, what makes this rule kind of difficult to figure out is you're going from adding to multiplying or from multiplying to adding. So logarithms have this kind of weird behavior. But if you can remember, the behavior is based on exponents behavior, right? If you're multiplying two things together, you add the exponents. If you're dividing two things, you subtract the exponents. So if you can keep that in mind, that the logarithms behave the way exponents would behave, I think that makes the rule make a little more sense. All right, so let's look at some examples of this. Here we have log base 5 of x plus 6 plus log base 5 of x plus 7. The directions are not very explicit here. They just say simplify, but what they want us to do is to rewrite this as a single logarithm. And so we will do that. We're going to add these two logarithms together into a single logarithm. So I'll go ahead and write log. The base stays the same. It'll be log base 5. And then we will put the x plus 6 and the x plus 7 inside of this single logarithm. And this is supposed to be plus here. And what are we going to do with the x plus 6 and the x plus 7 when they go inside the one logarithm is we will multiply them together. Because we were adding here, we want to multiply these together inside of this single logarithm. All right. And so that's simplifying it. Now, I'm not sure if MathXL will also want us to FOIL these together because you're multiplying these now. You definitely want to put parentheses around these when you go to multiply them. But I'm not sure if they actually want us to carry out the multiplication. But just in case they do, I'm going to go ahead and write that on the screen. And so we'll have x times x, which is x squared. X times 7, that'll be 7x. 6 times x will be 6x. And those will get those will get added together. So we add these together and we'll get 13x. And then 6 times 7 would be 42. So trying to do that quickly because at this point, I think everybody in this class should know how to FOIL pretty quickly. So now maybe you'll have to write it out in a little more detail than what I just did, but you should be able to get that result fairly easily on your own. And so we'll copy down the log base 5. And I'm using brackets here because we have parentheses inside the logarithm. So brackets just to make it a little easier to read. But since we no longer have parentheses here, I'll go back to just using parentheses as my container for what's inside the logarithm. And so this would be my final result. Here they're asking us to go in the other direction. We already have a single logarithm. They want us to split this up into separate logarithms. So the way they, I wanted to say express, but that's in the direction. So the way they describe that in the directions is to say express as a sum of logarithms. That means they want you to split it up into separate logarithms. So here we're multiplying the c and the d together. So what we want to do is split these up and put the c and the d in separate logarithms. So we will have log base 8 of c and log base 8. Let me rewrite that. I kind of didn't space that very well. Log base 8 of d. And what are we going to do with these separate logarithms? Because these are being multiplied here, we will add these logarithms together. All right. And that would be our final answer. So that is how you add logarithms together into a single logarithm, or how you take a single logarithm that has things being multiplied and split them up into separate logarithms. In this homework assignment, they'll be asking us to do both of these, and the examples get a little bit silly. But in the future, like in the next section, 4.4, this first example is very relevant, because if you're trying to solve an equation that has logarithms, you'll want to add your logarithms together into a single logarithm first in order to solve the equation. So this is actually really useful for solving equations. This one, the second one, maybe not so much. I can't think of too many examples where this is something you'll want to do, but it's something that they're going to have you practice in section 4.3 all the same. All right, so we talked about the product rule, and that rule exists because if you're multiplying two things together, you would add the exponents. Therefore, we add the logarithms. The next rule we're going to look at is the quotient rule, which I kind of alluded to earlier. And it's the case where if you're dividing two things, you would subtract the exponents. And so that's what you're going to do with the logarithms. So if you have log base a of m divided by n, you can split those up into separate logarithms. The m goes inside of its own logarithm. The n goes inside of its own logarithm. And then you will subtract those separate logarithms from one another. Right? And so you get log base a of m minus log base a of n. Let's see, what was I going to say about this? So, the rule works in reverse as well. So what I was going to say is you do have to be careful the order you write these in, because adding, it doesn't really matter. 5 plus 2 is the same as 2 plus 5. But for subtracting, it makes a difference, right? 5 minus 2 is not the same as 2 minus 5. So you have to make sure when you're subtracting that you do it in this order. It's the logarithm, how do I want to say this? The thing from the numerator is positive, the thing from the denominator will be negative, will be what comes after the minus sign. All right. And what I was about to say is that this rule works in reverse. So if you're subtracting two separate logarithms, you can rewrite that as a single logarithm by dividing those things inside of a single logarithm. And again, the order matters there when you're dividing. So make sure the thing from the positive logarithm goes on top, the thing from the negative logarithm goes on the bottom. All right, so let's take a look at a couple of examples for this. All right, so here we are being asked to write this as a single logarithm. So this one is a little bit more descriptive. We are subtracting these logarithms from one another. So to write this as a single logarithm, it'll still be natural log. I'll take the x to the 5th power and the x to the 3rd power, and because I'm subtracting, I will divide these when I put them inside the same logarithm. All right. And then I want to simplify this, and because now these are inside the same logarithm being divided, I can reduce this, or I can reduce that fraction, and it reduces to x to the 2nd power. And so that would be my final answer. For this second example, it's already a single logarithm. They want us to rewrite it as a difference of logarithms. So again, they want us to split it up into separate logarithms, which means d will go inside of its own logarithm. So I'll have log base 10 of d, and 10 will go inside of its own logarithm. And what will I do with these separate logarithms? I will subtract them. Because I'm dividing here, the logarithm should be subtracted. And then this one has a extra special step here. Log base 10 of 10 can be simplified. So if the logarithm you get with a number can actually be simplified, you should go ahead and simplify it. And so how many powers of 10 does it take to equal 10? The answer is 1. And so log base 10 of 10 simplifies to 1. All right, so we get that result. All right, so let's take a look at this example here, or these couple of examples. So these are going to get a little bit more complex. This first example isn't really any worse than the problem we just did. So in fact, why don't you take a moment to pause the video and try to do this first example on your own, and then resume the video to see if you came up with the correct result. So what we should be doing here, because we're dividing, we will put these in their own logarithms, right? So we want to split this up into separate logarithms. which means the x minus 9 will go inside of its own logarithm. It'll still be natural log. And the x will go inside of its own logarithm. And what you should have done with these two logarithms is you should have subtracted. Because we're dividing here, we want to subtract these logarithms. What you might have been tempted to do further is to try to split the x minus 9 up into separate logarithms. And maybe you might have come up with natural log of x, natural log of 9 in some fashion. But you can't go any further with this. This cannot be split up. So the reason I chose this example is to make this point. That you can split up a logarithm if you're multiplying two things together, or if you're dividing two things. Then the logarithm can be split up into separate logarithms. You cannot split up a logarithm if they're being added or subtracted. So this x minus 9 cannot be split up any further. It can only be split up if we're multiplying the two things together or if we're dividing the two things. So in fact, this is as far as you can take this problem. And that also is an issue with this example here. So here, we want to split this logarithm up into separate logarithms. But we can't do that if we're subtracting. It's the same issue that we had up here. We can only split the logarithm up if we are multiplying or dividing. So you might just give up on this problem and say, well, there's no multiplying or dividing happening here, so I can't do anything with it. Or you could try to find a way to rewrite it so that there is multiplication or division happening. X minus 9, you can't rewrite that in any other way. But x squared minus 100, we can rewrite that by factoring it. And when we factor it, we have two things being multiplied together. Then we can split the logarithm up. Right, so x squared minus 100 can be written as x plus 10 times x minus 10. So I can factor it. And factoring means you're rewriting it so things are being multiplied together. And now I want to take the log of this expression. And now we can split this up because now we're multiplying two things together. So I took the first step on this problem, but why don't you pause the video again and take it from here? See if you can rewrite this logarithm as two separate logarithms, and then resume the video to see if you came up with the right result. All right, so what you should be coming up with is log base 10 of x plus 10 in one logarithm, log base 10 of x minus 10 in the other logarithm, and what you should have chosen to do with those two logarithms is to add them together. Since we're multiplying here, we want to add the logarithms together, and then that's where you stop, because you can't split these up any further, because these are not being multiplied or divided. So this would be my final answer. All right, let's take a look at the last, well, there's two more rules, I should say. This is the last major one that kind of fits with the ones we've done so far. This is called the power rule. And this one is actually one of my favorite rules. Excuse me, I don't know what's wrong with my voice. I think, when I teach throughout the week, keeps my vocal cords loose. But when I'm sitting at home and not doing a lot of teaching, I think kind of tightens up my vocal cords a little bit, and it's a little bit harder to get going again. Excuse me. All right, so this is called the power rule, and like I said, it's one of my favorite rules. I think it's really neat how it works. So if you have log base a of m to the power of n, so if you have an exponent inside of your logarithm, you can bring that exponent down in front of the logarithm. You can bring it outside the logarithm by multiplying it in front of the logarithm. And then the rest of the logarithm just stays the same. So you bring the exponent from inside the logarithm, multiply it down in front of the logarithm. And so it's a really neat rule. The reason it works, so the justification for this rule is if so again, this logarithm here is how many powers of a it takes to equal m, right? That's what logarithms tell you. And if you want to take that m and raise it to the power of n, which is what you're doing inside of this logarithm, you would do the same thing to the left-hand side here. And what would you do with these two exponents? You would multiply these exponents together. And so that's why the n gets multiplied to this logarithm, because the logarithm is representing this exponent. That exponent would get multiplied by n in the case where you're raising it to the power of n. And so it's because when you have one power raised to another power, you multiply the exponents together. That's why we're multiplying these two things together here. So again, that's a quick justification for it. You don't have to know that in order to know the rule and to be able to apply the rule. Just remember that exponents inside of logarithms can be multiplied to the front of those logarithms. So let's take a look at an example. So here they want us to use that rule, but they have a radical here. So this rule only works on exponents, but we can rewrite radicals as exponents. So in order to do this problem, you'll have to know that a fourth root can be written as a 1/4 power, right? So the fourth root of 10 is 10 to the 1/4 power. That's still inside of this logarithm, but now that we have an exponent, we can use the power rule we just learned to multiply that exponent down in front of the logarithm. And so we can rewrite this as 1/4 times the natural log of 10. And then that would be our final answer. So that's a product. It's a weird one. It's, because it's multiplied. It's 1/4 times the natural log of 10. All right. So that's how the power rule works. Now this example down here, even though it's following the previous screen that we had, actually does not involve the power rule. But in order to get to more interesting problems that do involve the power rule, we have to kind of build up to it. And so what's going to happen here is we're going to split this logarithm up. We're not using the power rule here. We're just splitting the logarithm up into separate logarithms, just like we did before. Because we're dividing, we're going to split these two up into two separate logarithms. We'll have log base 2 of 11. So 11 goes inside of its own logarithm. The 4y goes inside of its own logarithm. And I kind of said it earlier, but now is when it's relevant. Because we are dividing, we will subtract these logarithms, right? So just like what we did before. But what's different with this problem is that now we can actually split this logarithm up again because we're multiplying here, right? So anytime you're multiplying or dividing, that logarithm can be split up more. This is 4 times y, so I can split this up into two separate logarithms again. The 4 will go inside of its own logarithm, so we'll have log base 2 of 4. The y will go inside of its own logarithm. And because we're multiplying here, I will add these logarithms together. Now here's where it gets a little tricky. This minus sign is going to get copied down, and that minus sign applies to this whole expression because we want to subtract this, whatever, we're subtracting everything that remains in this expression. So even when I rewrite it in a different way, we still want to subtract everything that remains. So we are subtracting the rest of this expression from log base 2 of 11. And so that minus sign has to be distributed to these two new logarithms that we just created. And so I'm going to distribute it, sorry, that didn't do a good job of drawing that arrow, to these two logarithms. And so we will end up with minus log base 2 of 4 minus log base 2 of y. And then again, this log base 2 of 11 just copies down. It's still positive. And so what I want to point out is there's a shortcut that we can use here. So when we're going to split this logarithm up, anything that's being multiplied or divided will get to go inside of its own logarithm. So the 11 goes inside of its own logarithm. The 4, which is being multiplied to the y, those will get split up as well, and each one will go inside of its own logarithm. And then we will decide whether the logarithm's positive or negative based on whether it came from the numerator or from the denominator. So anything that comes from the numerator will go inside of a positive logarithm. Anything that comes from a denominator will go inside of a negative logarithm. And that way we don't have to do it one piece at a time and have to distribute a negative sign. We can just jump to the final result. 4 was from the denominator, so its logarithm is negative. Y was from the denominator, so its logarithm is also negative. And that way we can just jump right to here instead of having to do it one thing at a time. Whoops, okay, I really messed that up. I meant to undo, but I accidentally went forward a page. I don't know why I got those confused. But the problem with this software is once you switch to a page and come back to it, you can't undo what you just did. So I'm stuck with this line where it's at, so I'm sorry. In fact, I mean, I shouldn't be putting a box around this even because I'm not quite done. I wanted to make the point I just made with this, but then to finish the problem, we actually have one more thing to do, which is this log base 2 of 4 can be simplified. So log base 2 of 11 cannot be simplified any further. How many powers of 2 does it take to equal 11? There's not a good answer for that, so we'll just leave it as a logarithm. But how many powers of 2 does it take to equal 4? There is a nice answer for that, and the answer is 2. So my final answer here is going to be log base 2 of 11, since I can't simplify that one, minus log base 2 of 4, which is just 2. It simplifies to 2, because how many powers of 2 does it take to equal 4? The answer is 2, minus log base 2 of y. And so this would be my final answer. Let me make sure I can write this one correctly here. All right. Oh, I still kind of messed up at the end there. Okay, one more time. Okay, I'm just going to do this. There we go. Okay. And so that would be my final answer for that problem. All right, so let's take a look at these more complicated looking problems. These aren't actually as bad as they might look if you use the shortcut that I just described. Now, before I can use the shortcut here, I need to rewrite my radicals as exponents so that I can use the power rule that we talked about a few screens ago. All right, so I'm going to rewrite this as natural log of xy to the 1/5 power, right? A fifth root is a 1/5 power. We saw earlier a fourth root is a 1/4 power, so hopefully you're catching on to the pattern. A cube root is a 1/3 power, a square root is a 1/2 power. On the bottom here, we already have this as an exponent, but this is also a radical. This is a cube root, right? So if the denominator is a 3, that's a cube root for your exponent. All right, and so this 1/5 power applies to both the x and the y. And so I use parentheses here to show that this x, y were both inside of that fifth root, but we can apply that fifth root to each factor separately. And so we'll get natural log of x to the 1/5 power, y to the 1/5 power, over t to the 5/3 power. All right, I'm sorry, I'm not doing a good job writing today for some reason. Okay, so now we're ready to take this big shortcut that we just talked about. So we want to split all of this up into separate logarithms. The x, the y, and the t will all go into separate logarithms since they're all being multiplied or divided. And so I will go ahead and jump to that result. The x will go inside of its own logarithm. The y will go inside of its own logarithm. And the t will go inside of its own logarithm. The exponents on each of those, we will use the power rule for each of them, and each of those exponents will go in front of the logarithm for that particular variable. I'm trying to think of the best way to say it. So let me maybe just do the example here. This power of 1/5 will go in front of the logarithm containing x, right? So this 1/5 power was on the x, it will go down in front of the logarithm containing x. This power of 1/5 on the y will go in front of the logarithm containing y. This power of 5/3 on the t will go in front of the logarithm containing t. Right, so each exponent will go down in front of its individual logarithm that was created for that particular base. All right, I don't know if I'm describing that very well, but hopefully you can see the pattern here. So each exponent goes in front of each individual logarithm. And then the last thing we'll decide is, should these logarithms be positive or negative? So if the logarithm is being generated from something from the numerator, that logarithm will be positive. If it's being generated from something in a denominator, that logarithm will be negative. So for x, that's from the numerator, that logarithm will stay positive. The y is also from the numerator, so that logarithm will also be positive. The t is from the denominator, so that logarithm will be negative. And this will be my final answer. So it's just a shortcut to jump to this answer. You could do it one piece at a time. You're dividing here, so you would subtract the separate logarithms. But then in one of the logarithms, you'll have x times y. Since you're multiplying, you'll split those up and you'll add those logarithms. And then in each of those logarithms, you'll have these exponents. So you'll bring those exponents down in front of those logarithms using the power rule. But you would have to do that one step at a time, and it would take like 3 or 4 steps to do each thing individually. This is just doing all those steps all at once. All right. Let's do the same thing with this problem, except it's in reverse. We want to take all these separate logarithms and to rewrite them all as a single logarithm. And so I will start by writing a single logarithm. I'll have log base p, because that's the base they're using here. I'm going to have one giant logarithm here. I'm going to make a fraction because I have some positive logs, some negative logs. That means some things will go in the numerator and some things will go in the denominator. So I'm going to go ahead and make a fraction to get ready for that. If the thing is in a positive logarithm, it will go in the numerator. So s is in a positive logarithm, so s will go in the numerator. T is in a positive logarithm, so t will also go in the numerator, multiplied to s. Y is in a negative logarithm, so y will go in the denominator. And a is also in a negative logarithm, so it will go in the denominator as well, multiplied to the y. Then you go back and grab all these numbers in front of these logarithms, and those become exponents on each of these variables, right? So 3 becomes an exponent on the s, 1/2 becomes an exponent on the t, 3/2 becomes an exponent on the y. Do not include the negative with that because we already dealt with the negative sign. The negative sign is why the y is in the denominator. So we don't also want to use the negative sign on the exponent as well. So you can't use it both times. So we already used the negative sign to put the y in the denominator, so we don't need to use it again for the exponent. And so the exponent will just be 3/2 on the y, and the exponent will just be 3 on the a. And this will be my final answer. And that's putting it all together at once. So instead of doing it 2 things at a time, right? Putting the numbers inside the logarithms first to make them exponents, then adding these logarithms together and writing that as a single logarithm and multiplying the s and the t together and then subtracting. You could do it one thing at a time. If you look at Math Excel at the example, that's how the examples will do it, is it'll do one thing at a time. And you'll see it's multiple steps. It doesn't need to be that complicated. You can do it all at once if you follow these rules that I'm giving you. All right. So let's take a look at a couple more. We have a couple more types of problems to look at. One of them is solving exponential equations by using logarithms. This is actually technique number 3. So this is part of the string of mistakes I made with numbering these techniques. So technique number 1, if you remember, we saw in 4.1, is if you have an exponential equation, try to rewrite both sides as exponents with the same base. If you can do that, that is the best way to do the problem. But you may not always be able to do that. Sometimes you won't be able to rewrite both sides as an exponent. So we saw in 4.2, another technique is to take the equation that's in exponential form and rewrite it in logarithmic form to solve the equation. So if you can't get both sides to be the same base, you can rewrite the equation as a logarithmic equation, and that will help you solve the equation. That was technique number 2. Technique number 3, if you have an exponential equation where you can't rewrite both sides with the same base, is to apply a log to both sides, either a log base 10, right, because the base isn't written here, so that's a log base 10, or a natural log to both sides of the equation. Now, I remember when I first started teaching that I preferred to use natural log on both sides. It's just less writing. But my students didn't really like natural log. It seemed more difficult to them. They were more confused by natural log. They were more comfortable with log base 10. So I've switched my habit to that. So now I use log base 10 on both sides. The reason we're using log base 10 or natural log is so that we can type our answer into our calculator to get an approximate answer. So this is a technique that you want to use if you want to be able to type your answer into your calculator, because everybody can do log base 10 or natural log on their calculator. Then use the power rule to bring the exponent that you're dealing with in front of the logarithm. So that brings it from the air down to the ground where you can solve for that variable. and then you can solve it for x. And because you're using one of these two logarithms, once you've solved it for x, you can type it into your calculator to get a decimal approximation. All right, so let's take a look at this example. Let's take a look at an example of this technique in action. So here we have, find the approximate solution. So notice they want us to find an approximate solution, which means we want a decimal answer here, which means we have to be able to type it into our calculator to get a decimal answer. So if you use the technique that we learned in section 4.2, I'm going to go ahead and do that here so you can see what that looks like. I can't write both sides with the same base. I can't rewrite 7 as 2 to some power. If I could do that, that's the way I would do this problem. But it can't be done here. So that technique's not going to work. So what we learned in section 4.2 was to rewrite this equation in logarithmic form. I'll start by writing log. The base is the base. So the base of the exponent becomes the base of the logarithm. I skip over this part. The logarithm equals the exponent. So the exponent here is x, which means the 7 is what goes inside the logarithm. So that's what we learned to do in section 4.2. And this is the solution to the equation. But this gives me the exact answer in logarithmic form. It doesn't give me the approximate answer that I can write as a decimal. My calculator that I have on my computer does not let me type in log base 2. And so I cannot type this into my calculator to get a decimal answer from it. So it's not wrong. This is the solution to the equation, but it's the exact solution. And I have no way of generating the approximate solution from that. My calculator doesn't let me do that. And so what we're learning to do in section 4.3 is to solve this equation in such a way that I can type it into my calculator. So I'm going to leave a little space here in front of the 7. And the technique that we were just talking about is to apply a log base 10 to both sides of the equation. So I apply a log base 10 to the left-hand side. I apply a log base 10 to the right-hand side. So I'll put parentheses around these two things. I'm doing the same thing to both sides of the equation, so it's perfectly balanced. And now I can use the power rule that we just learned to bring this exponent and multiply it down in front of this logarithm. So that takes the variable x, which was stuck in the exponent, and brings it down to the ground level, where then I can solve it by using my usual methods, adding, subtracting, multiplying, dividing, right? And so this is what we end up getting. All right. And so the x goes down in front of the logarithm. It's being multiplied to the log base 10 of 2. And now I can solve for x by dividing, right? So we're multiplying by this log base 10 of 2. To cancel out a multiplication, we use division. Now in section 4.2, I cautioned you not to divide by an empty logarithm. But this is not an empty logarithm, right? There's a number inside of that logarithm. So this is a perfectly sensible mathematical operation. And we are using division to cancel out a multiplication. That's the proper way of using a division when you're solving equations. So if I do that to the left-hand side, I do the same thing to the right-hand side. As long as there's a number inside the logarithm when you're dividing, it's okay to do, right? So these logarithms will cancel each other out, and I will get x equals log base 10 of 7 divided by log base 10 of 2. Now this is still an exact answer, right? It hasn't been plugged into our calculator yet, but it's something that I can plug into my calculator because the base here is log base 10, and most standard calculators, scientific calculators, will have log base 10 as a function. It's one of the buttons on your calculator. And so let's go ahead and pull up the calculator here on my computer, and we'll go ahead and type this into our calculator. So we have log base, okay, sorry, I forgot this calculator does it backwards, right? I think we talked about this in a previous video. I have to type in the 7 first and then do log base 10. Most calculators, like if you have a TI 30 something, 32 or higher, you should be able to type log of 7, just like you see on the screen. But some calculators make you do it like this. So you might have a calculator, if it's one of, if it's an older one, for example, like a TI 30, I believe, you have to type the number in first and then type log in second. And that's what I'm having to do here. And it's a little bit weird to have to do that way. But so I type in the 7 first, then I type in log base 10, and that gives me the decimal approximation for log base 10 of 7. I want to divide that by log base 10 of 2, so I have to type in the 2 first, and then type in log, and you see that now it's going to divide by log base 10 of 2. This is not the answer. I still have to enter to actually carry out that division. So what you see on the screen right now is log base 10 of 2. That's the decimal for that. But then to divide those two, I have to go ahead and hit equals, and that's going to give me this answer here. And while it doesn't say it on the screen, on Math Excel, it always asks for these answers to be to 4 decimal places. And so I'm going to round it to this decimal place here. This is the 4th decimal place. Because this is a 5, I'm going to round that up to a 4. So my answer is 2.8074. Let me see if I can remember that. 2.8074. And so this is my approximate solution, which is what they were asking for. So this is exact still because it's in logarithmic notation. This is approximate because it's a decimal that we had to round. And so now it's an approximate solution. All right. Why don't you give this one a try? It's a little bit more difficult because of the 4 that's there, but give this one a try anyway. So pause the video, try to solve this equation using the same technique. Not this technique, sorry. This technique right here. And then resume the video to see if you came up with the correct answer. All right, so what we're going to do is we're going to apply a log base 10 to both sides of this equation. So I apply a log base 10 to the left-hand side, apply a log base 10 to the right-hand side. This allows me, by having a logarithm here, it allows me to take the exponent, multiply it down in front of the logarithm. So I will have 4x times log base 10 of 1.83 equals log base 10 of 3. Now that x is down on the ground level, I can solve for x. In this case, I will again divide to get x by itself. So I'm going to divide by log base 10 of 1.83. And the same thing on this side, log base 10 of 1.83. And if that's all I do, it cancels out the logarithm, but I will still have a 4 in front of the x, which I will then need to get rid of. And how do I get rid of this 4? I also divide, right? I divide by 4 to cancel out this 4. Well, why not do that while we're taking care of the logarithm? We can just go ahead and take care of both of these at the same time. So I will also go ahead and divide by 4 on both sides. And so that's going to cancel out the 4s, cancel out the logarithms, and I'm running out of space here. So I'm going to get x. So this is my exact answer, which notice I haven't typed anything into a calculator yet. So you're going to have that temptation of, you don't like logarithms, they're unfamiliar to you, you feel more comfortable with decimal numbers. And so you might be tempted to, for example, type log base 10 of 3 into your calculator right away and get a decimal number for this. But the problem with that is now you're working with an approximate result, right? And so if you type this into your calculator, you get this run on decimal, you're not going to want to write out 10 decimal places for that number. So you're going to round it off. Even 10 decimal places is rounding it off, right? But you'll probably be tempted to round it off to 2 or 3 decimal places, or maybe even 4. You might think that's enough. The problem is if you round this off early in your calculation, and then you round this number off early in your calculation, and then you divide those rounded off numbers, your answer is not going to be precise enough because you're using inexact figures to try to get this result, which even if these are accurate to 4 decimal places, when you divide those results, it might not be accurate to 4 decimal places anymore. And so you really should keep the logarithms as long as possible. Keep the answer exact for as long as you possibly can. And then at the very end, after you've solved it for x, type it all into your calculator at once. And so my final answer here in exact form is going to be log base 10 of 3 on top divided by 4 times log base 10 of 1.83. So this is still exact. And now I will type this into my calculator to get my approximate answer to 4 decimal places. I've seen it happen to students where they round this one off, they round this one off. They solve it for x, they do all the steps right, but because their numbers were rounded off early, their fourth decimal place isn't exactly what it's supposed to be. Or maybe even their third decimal place isn't right. And so Math Excel is going to count it wrong. That's why it's asking for 4 decimal places, to really force you to keep the logarithms in your calculations as long as possible. All right, so when I go to type this into my calculator, I'll need to be careful in how I do that. So on top, I have to do it backwards, which makes this even more difficult. 3 log base 10 of that gives me log base 10 of 3, divided by, now on paper, it's fine to write like this, but when you go to type this into your calculator, especially if you're typing it in all at once, you have to use parentheses for this denominator, right? So in my calculator, I'm going to have to write this. I'm going to have to write or type it in like this with the denominator in parentheses. If you don't do that, when it does order of operation, it will divide by the 4, but then that's all it will divide by. And then it'll see times this logarithm, and it's going to multiply by log base 10 of 1.83 instead of dividing by log base 10 of 1.83. And so in order to make sure we're dividing by both of these, we have to put them in parentheses. All right. And so I will divide by parentheses 4 times, and now I want to do the logarithm, but I have to type in the 1.83 first, 1.83 log base 10 of that, and then close the parentheses. All right, so it needs to look like this in your calculator in order to get the right result. And so I'm going to hit enter to get my final result. And so what you should have gotten was 0.4544. And then the 8 is going to tell me to round this up to a 5. So when I round this to the 4th decimal place, it'll be 0.4545, which should be easy enough for me to remember. I think that's the right answer. I don't know. Now I'm questioning, do I need to hit enter again? Because maybe I just got the parentheses part. Let me try hitting enter one more time. I don't know. I feel uncertain about this, honestly. No, okay, so now you see it got more complicated. Yeah, so I think I was right the first time, and I'm trying to remember back to previous semesters. This answer feels like it is the right answer. So 0.4545. Hopefully I'm right on that. So check me on your calculator. And if I'm wrong, send me an email. I don't know how I'm going to be able to fix this video. Maybe I could add something to the end of it to correct myself and then re-upload it. But I believe that's the correct answer. All right, but make sure you're typing it in like that, and you should be fine. All right, so one more type of problem to talk about. It's a quick one, and it's on this thing called the change of base formula, which you will want to know, especially if the calculator you have does not let you type in whatever base you want, which is going to be most of us. So it turns out that if you have a base that you can't plug into your calculator, you can actually change it to a base that you can plug into your calculator by using this formula. And really, we developed this formula on the previous problem. So if you look back at this example here, this answer and this answer are both the exact solution to this equation, which means these are equivalent to each other. This is log base 2. These are in log base 10. So this gives us a bridge for changing our base from base 2 to base 10. And so notice the pattern here, that the base of the original logarithm becomes the thing inside the logarithm in the denominator. And so we keep the 7 in the logarithm on top. The base of our original log goes in the logarithm of the denominator. And the new base can be whatever we want. And so we choose base 10 so we can plug it into our calculator. Right? So this can be any base we want. It's not based on whatever's over here. So we choose base 10. The 7 stays in the logarithm on top. The original base goes in the logarithm on the bottom. And now we have something we can type into our calculator. Right? So that's how this change of base formula works. The m stays in the logarithm on top. The original base goes in the logarithm on the bottom. And the new base is anything we want it to be. And so we will choose log base 10 so we can plug it into our calculator. And so that's how we can evaluate this logarithm, right? So my calculator doesn't do log base 2, but I can use this change of base formula to change it to log base 10 so that I can plug it into my calculator, right? So this will be log base 10 of 11, right? The 11 will stay in the logarithm on top, divided by log base 10 of 2. The original base goes in the logarithm on the bottom, and the new base, I got to choose to be whatever I want, so I chose for it to be base 10. And now I can plug this into my calculator to get the approximate value of this logarithm. All right, so let's go ahead and do that real quick, and then we'll be done. So we have 11, log base 10 of 11 is going to be this, divided by log base 10 of 2, and I get this result, 3.4594. The 3 tells me to keep that as a 4. I round it down, so it's going to stay 4. So help me remember this, 3.4594. Okay, 3.4594. Let me just double check to make sure I wrote that right. Okay, 4594. Okay, perfect. And that would be our approximate value for that logarithm. All right, so this concludes the lecture on section 4.3. Thank you for watching. If you're one of my students and you have any questions, please contact me and let me know.